So you could use, again, that molar mass is used to go from grams to moles or moles to grams. What if we have molecules and going from moles to molecules? Well, we're going to get Avogadro involved again. So Avogadro's number, it's there again, 6.022 times 10 to the 23rd molecules per mole. Now, the last time we saw it as atoms per mole. And I told you would see it again, and it's actually representative particles per mole. So that means it could be atoms, it could be molecules, it could be ions, it could be formula units. We're going to use it for this class as molecules for per mole for this section. So anytime you see the word molecule anywhere in a problem, you are going to have to use Avogadro's number, and that's going to be our key indicator there. So let's try this problem right here. How many molecules are equal to 10 moles of carbon dioxide? I see the word molecule, so I'm going to have to use Avogadro's number. And it goes from molecules to moles and moles to molecules. So I start with the number given in the problem, 10 moles of carbon dioxide. I can write that formula there. Now I need to go to molecules. I'm going to have to use Avogadro's number. Can I use it now? The answer is yes, because as long as you have either molecules or moles in this position right here, you can go ahead and use Avogadro's number. And if you always ask that question, it'll keep you on track. So I'm going to go ahead and use it. Mole is here in that top position of our dimensional analysis, so mole has to go here. And remember, it's 6.022 times 10 to the molecules in 1 mole. So in 1 mole, there are 6.022 times 10 to the 23rd molecules of carbon dioxide. It's actually of anything, but this time we're talking about carbon dioxide. Remember, when you use Avogadro's number, the answer will probably come out in scientific notation. Make sure you look to the end of your calculator to get all the points you want. Again, sig figs, look at the number given in the problem, and that's 3. So I need 6.02 times 10 to the 24 molecules of carbon dioxide. That's a lot of molecules. All right. Well, just like we did when we worked on these conversions before, we can combine them together. And we can use both molar mass and Avogadro's number in a problem like this. Similar problem, how many molecules, I see that key word, I know I'm going to have to use Avogadro's number, are in 10 grams of carbon dioxide. So this one is a little different. So if I start with 10 grams of carbon dioxide in my dimensional analysis, I know I have to use Avogadro's number because I see the word molecule here. And you ask yourself, can I use it now? The answer is no, because you have grams here. You can only use Avogadro's number if you have molecules or moles in that top spot. So what we're going to have to do in order to solve this problem is first convert grams to moles using molar mass, and then moles to molecules using Avogadro's number. So let's find the molar mass of carbon dioxide. It has 1 carbon and 2 oxygens. Carbon is 12.01 from the periodic table. Oxygen 16 from the periodic table. Add that together and you get 44.01 grams of carbon dioxide in 1 mole of carbon dioxide. So now we're going to use that. Grams are here, so grams have to go here, and that number is going to be tied to grams. Remember, you'll never write down 1 gram. You'll also never write down 1 molecule. There are 44.01 grams in 1 mole of carbon dioxide. Grams cancel. Now, can I use Avogadro's number? Because I got to get to molecules. Yes, because I have moles right here. Mole is right there, so mole has to go right here. And in 1 mole of anything, there are 6.022 times 10 to the 23rd molecules. Of anything, we're talking about carbon dioxide here. Everything on top multiplied together, divided by everything on the bottom multiplied together. So I need 3 sig figs in my answer. 1.37 times 10 to the 23rd molecules of carbon dioxide. And that's how you do these problems. Now, starting with different things. I could have you go from molecules to grams. But again, you're going to use Avogadro's number and you're going to use molar mass. And we have to be able to use them backwards and forwards. All right, last thing in today's video cast is percent composition. Now, composition means what something's made up of. So we're looking for percents here. Now, you never want to be confused about what a percent is. A percent is always part over whole times 100. That's how we get percentages of everything, and this is no different. The formula, or the working formula that we're going to use looks like this. It is the mass, and when I mean by mass, it's the molar mass of what you're looking for. So if we're looking for oxygen, it would be the molar mass.
Call the office. Coach Lawrence, please call the office. Jackson Whiting, please come to the office. Jackson Whiting.
It's the molar mass of whatever the element is that you're looking for, of all of those. So the molar mass of what you're looking for over the molar mass of the whole compound times 100. And that's how you're going to find the percent of element in a compound. So we'll practice with this one right here. Find the percent composition of oxygen in sodium nitrate. Well, first, the easiest thing to do, and where I like to start, is right here, the molar mass of the whole compound, because that's easy and we know how to do it. So sodium, I have one of those in sodium nitrate. Nitrogen, I have one of those. And oxygen, I have 3 of those. Sodium from the periodic table is 22.99. Nitrogen is 14.01 grams per mole. And each oxygen is 16. I add all that up together, and okay, and I get a molar mass of 85 grams per mole. All right, so that's the mass of the whole thing. Now, I need to find the percent oxygen, I need to take the mass of all the oxygens. Well, in this particular compound, there are 3 of them. 3 times 16 is 48 grams per mole. So that's what's going to go on top, the mass of all my oxygens, because that's what I'm looking for, grams per mole, over the mass of the whole thing, which we calculated, 85 grams per mole. And then all of that times 100. Well, grams per mole divided by grams per mole, those cancel out, and all you're going to end up with units is a percent sign. And so 48 divided by 85 times 100 is 56, and we'll just go to 1 decimal place, 56.5% oxygen. So that's a lot of oxygen in that particular compound. Now, sometimes when you do these problems, they don't give you an element to look for. In this example, I gave you an element to look for, but not always will that be the case. They'll just say, what is the percent composition of sodium nitrate? When they say that, they want each element. So, if I were going to find the percent nitrogen next, again, part over whole times 100. The part I'm going to be looking for in this case is the nitrogen. I only have one of those, so I put 14.01 up here, grams per mole, divided by the mass of the whole thing, which is 85 grams per mole, times 100. And I'm going to end up with 14.01 divided by 85 times 100. And that gives me 16.5% nitrogen. Okay, if I wanted to find out how much sodium there was, I could run through this same process and I would just put the mass of all the sodiums in this top spot, and that would find the percent sodium. Or what I could do is, remember, all percentages have to add up to 100 because it makes a whole compound. So I could say 100 minus 56.5 minus 16.5, because this is the oxygen, this is the nitrogen. The only thing that will be left is the sodium. And then I could calculate it that way, 100 minus 56.5 minus 16.5. And I end up with 27% sodium, doing it that way. All right, so that's how you use molar mass as a conversion factor, and how to do percent composition.